Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, does she have a robotic thumb? And how does that thing work?
Hello everyone, and welcome to Robot Talk. We're live at the Great Exhibition Road Festival in London for a very special episode of the podcast. I'm your host, Claire Asher, and today I'm chatting to Milia Hasbani, Benjamin Metcalfe, and Dani Clode about robotic prosthetics and human augmentation. My first guest for today is Milia Hasbani, a researcher in assistive technology at Imperial College London. Her work focuses on control of active prosthetic arms, combining user intention for wrist movements with a computer vision system for dynamically selecting the grasp type. So please welcome to the stage, Milia Hasbani. Hi Milia, welcome to Robot Talk.
Hello, thank you for having me.
So first of all, for members of the audience that might not be familiar, can you explain the difference between active and passive prosthetics?
Yeah, so as you'd imagine, there are lots of different types of prosthetics, and the user might have a different one based on their needs, their comfort levels, and sometimes even their budget. So passive prostheses don't have moving parts. They just are there, basically. The most common type, if you're thinking of arm prostheses, would be like a cosmetic arm. So it looks like an anatomical arm, and the user can have it there to support objects, to like hold a bag, for example, and it might help them feel more comfortable in certain social situations, but that's up to their preference. And sometimes they might have a different attachment that doesn't look like a hand, but can be used in different activities, for example, to hook onto a bike or to do yoga or specific sports. Active prostheses, on the other hand, do have moving parts. So you might be able to control these in different ways. So one example is having a hand that opens and closes. And one way to control this would be a body-powered prosthesis. So the user might have a strap around their shoulders, and when they move their shoulders, this would pull on a cable that would close the hand, for example. They could be powered externally using batteries and motors, and this is what you would think of as bionic arms, more robotically looking. And so in this case, you might control it by having electrodes on the arm that read the user's intention and then control the movement of the hand, for example. And this could be applied to like the leg, for example, an active knee, an active ankle, things like that.
And so that's kind of where your research comes in. You're working on the control of active prosthetic arms. And we've got a photo, actually, of a system that you're currently working on. So can you tell us a little bit about this system and how you're able to, work out what a user wants to do and actually translate that into movement?
Yeah, so as you mentioned, I work on like bionic arms. This is an example of my research here. You can think of the system as having three moving parts. So you have the wrist that can move, you have the hand that can open and close, and you can control the fingers in terms of which grasp type you want to use. So as I was mentioning, we would have electrodes on the surface of the skin. And these would read the electrical activity that's being generated inside the muscle. So this is the signal that's coming from the brain down through the nervous system to the muscle with the instruction of what movement the person wants to perform. And what we're reading here is called electromyography, or EMG for short. And that's the overview of the signals that are being generated in the muscle. And so what we can do with that signal is we can pass it onto the system and we can train it, so we can teach it. If this signal is generated, then we want to move in this way, for example. And in most available systems, it's a bit more simple. So you'd have one movement group that's active, and that might cause a specific movement like closing the hand. And then the opposite muscle group would be active, and that would switch into an open. So you sort of have a switch system, on in one direction, on in another direction. But in our system, we're looking at having more continuous and complex movements, moving the wrist while closing the hand, dynamically changing how much you want to move, things like that. And then also in commonly available systems, if they do have different grass types that you can use, which not all of them do. The way that this is chosen by the user is by cycling through one grass type to the other. So they might press a button, or they might like co-contract, and they'd have to go, okay, now I'm in a pinch, now I'm in a general grasp. So what we were thinking, not everyone can do this, and it's an added, extra effort. Yeah, it's extra effort from the user. So what we've done is we've added a camera that you can kind of see in the picture, and it's on the palm of the hand, and that looks at the object in front of it and decides potentially which is the most appropriate grass type to use based on which part of the object it's looking at. So it's not just the shape. It's not like, oh, I see a pen, I'm going to use a pinch. It's more thinking about which part of the object you're looking at, what the shape is, and how you might use it. Mm-hmm. So if you imagine like a bottle, if I was to go and drink from it, I might reach from the side, grab from the bottom. If I wanted to open it, I might place my fingers in a different way. And we do this without thinking about it. But for someone using prosthesis, there's different steps they have to go through to decide what they want to do, lots of different decisions. So what the camera does is, helps with this decision making, automatically chooses which grass type might be most appropriate, and makes that a bit easier, hopefully, for the user.
Amazing. Yeah, it's really interesting thinking about all the steps you have to go through to make these technologies more user-friendly and more kind of, like I said, fluid in the environment, I guess.
Yeah, exactly, because it's all about that thought process and how easy is it to use something, and how much do you have to train to get something right.
Yeah. So much of this we just do implicitly without thinking, so.
Definitely.
Okay, I'd like to invite my second guest today to come and join the conversation. Benjamin Metcalfe is a biomedical engineer who specializes in neural interfaces and implanted devices. He's interested in exploring the collision between technology and biology, and the extent to which engineering can be used to augment and enhance human performance. Please give Ben a very warm welcome. Hi Ben, great to have you on the podcast.
Hi, thank you for having me. Wonderful to be here.
So you're the Deputy Director of the Bath Institute for the Augmented Human. So can you give us a bit of an overview of the kind of research that's going on there?
So the Bath Institute for the Augmented Human is a fairly new research institute at the University of Bath. We comprise about 30 core academics, 60 affiliate members taken from across almost every discipline at the university. So this is the range from engineering, health, psychology, computer science, management, policy, etc. And the institute really has two goals. It's to continue the development of technology, which has traditionally been used for rehabilitation in healthcare applications, and then also to consider how this can be applied in enhancement, so going above an individual's baseline performance across a diverse range of sectors. So we're not just thinking healthcare, we're also thinking sports, defense, consumer. And as the technologies move from a healthcare setting into those alternative and often consumer settings, considering the regulatory, ethical, and policy changes and constraints that would need to be put in place as a big part of that.
I'm sure, yeah. And so one project you've worked on is a hybrid exoskeleton, which combines a robotic exoskeleton with muscle stimulation. And I've got a video of that, which I'll play in a moment. Can you tell us a bit about this project and talk about some of the potential applications?
Yeah, I can. So one of the things that we're interested in doing in bringing different disciplines together is to try and see the benefits where we have synergies across different domains and different technologies. So exoskeletons generally always are exterior only, so they're wearable devices and they use motors or actuators to move, say an upper limb or a lower limb in some of the videos shown here. But they don't activate the body's own muscles. So if you're trying to rehabilitate from, say, stroke, you might have the physical support and the movement, but you don't have synergistic activation of the muscles. There are alternative technologies called functional electrical stimulation, where we actually stimulate the muscles and we get real activation and movement, but it's quite poorly constrained. It's quite hard to get realistic movement. So we've done work where we've combined these technologies together using both an active support with the exoskeleton and specific stimulation of muscle groups to try and maximize the benefits in a rehabilitation setting.
Amazing, yeah. I mean, I often think of exoskeletons as something that an able-bodied person would use to augment their abilities, but it's fantastic to hear that it can also be used for rehabilitation. So my third guest today is Dani Clode. Dani is an augmentation and prosthetics designer at the Plasticity Lab at Cambridge University. Her work investigates the future architecture of our bodies, challenging the perception and boundaries of extending the human form. Please welcome Dani to the stage. Hi Dani, lovely to have you on Robot Talk.
Thank you for having me.
So you've designed a 3D printed thumb extension, which you're actually wearing now, that attaches to the hand and is controlled by your toes, called the third thumb. So tell us about this project and what inspired you to do this.
Yeah, sure. So this is my third thumb. So it's a 3D printed extra robotic thumb that's attached to my hand. It's controlled with my toes. So underneath my big toes is some pressure sensors, and it's enabling me to move it in these 2 degrees of freedom. And the project's actually working in collaboration with the Plasticity Lab at Cambridge University at the moment. And we're looking into using it as a model to understand kind of the boundaries of neuroplasticity and the effects of augmentation on the brain and body. So I'm part of kind of multiple neuroscience studies using the third thumb to kind of explore the brain.
So cool. My immediate question, if it's controlled by your toes, can you use it while you're walking? Does that
not you actively use it when you're walking, but I can, it's not so good for a podcast, but yes, I can kind of walk whilst not triggering it because it's kind of customized for my kind of walking, and then kind of choose to actively use it whilst I'm walking around. Yeah.
So you could kind of lock it in place to carry like a carrier bag or something?
Not just, well, yeah, you just kind of do an active press, but yeah, that's kind of like a third control that I'm looking into, yeah, for sure.
Cool. And you're also a collaborator on a project called the Alternative Limb Project. So what's that all about?
Yeah, so the Alternative Limb Project is run by Sophie de Oliveira Barata. And the project is really about designing kind of prosthetics that really kind of extend the wearer and extend kind of the wearer's personality a bit more. So yeah, I've collaborated on 4 prosthetic arms for a model in disability rights activist Kelly Knox. So this is one of them here, is the materialized arm. And this was to kind of really challenge the materials chosen for prosthetics and ask kind of why not? Why not this? Yeah. So we did kind of over 30 different materials. These are also all interchangeable, so you can take each chunk out and replace it with different materials. Cool. And then we also did an arm called the synchronized arm, which was completely clear. I don't know if you have a photo of that. Yeah. So this one, it was actually our first collaboration. And so Kelly was actually born with one arm. So she's a congenital one-hander. So she was actually born her whole self. And she actually chooses to not wear a prosthetic in her daily life. And so for this kind of design kind of concept, it was really about exploring her relationship with this technology. And so we put her heartbeat in the wrist. Oh, so it actually ticks in time to her heartbeat and can continue to tick when she's not wearing it. And so that was to really kind of reinforce this kind of relationship with this kind of object. And then we also did the vine arm, which is quite a weird kind of tentacle prosthetic. And so this is a robotic tentacle, and it's got 4 degrees of freedom. So it's also controlled with her toes. You can see in her on her shoes there. And this was to really kind of just challenge the kind of what a prosthetic is or could be. Yeah.
I love the idea of taking something that's so often just functional and making it art, making it something beautiful, an expression of who you are as a person.
Yeah, so these pieces are actually all in museums at the moment. So they're not kind of meant to be like a daily wear prosthetic, but yeah, more of a kind of statement piece.
Yeah. Okay, so now let's open up the discussion to everyone on the panel. And we'll start taking audience questions in a few moments. Okay, so I'd like to start the group discussion with a little bit of a philosophical or psychological conversation about the experience of wearable technology. And you all work with people who have tried to wear these devices in their various forms. How do you find that people relate to their robotic prosthetics? Do you find that they kind of quite quickly start to see the technology as part of themselves, part of their identity, or does that take a long time? Does it never happen? You're shaking your head down.
So most of the people I've worked with never really develop that true sense of embodiment with a prosthetic. Most of them will view it as a tool. They will use and abuse it. They will find ways to repair it themselves, and they think of it just as an addition. One of the bits of work we did was around sensory feedback. So very rarely will a prosthetic include any kind of sensory feedback to the user about how hard, for example, a hand is gripping. Now, as an engineer, we always, we go very deep and technical, and we want to produce something that moves in the same way as the human hand. We did some studies where we spoke to individuals about their prostheses, and the feedback we got was, well, I can't feel it, so I don't trust it. And if I don't trust it, I won't play with my animals and I won't play with my children. And so immediately that any chance of kind of embodiment is lost if you don't first of all have trust.
Yeah, that's really interesting because I think so many things that we interact with in daily life do give us feedback, whether it's a games controller or my phone. And I start to sometimes feel a little bit like my phone is an extension of myself. Like I will try and do gestures on a book or things that aren't my phone because it just sort of feels like it's, but that gives me feedback. So yeah, that's interesting that you highlight that as an important point.
So our first study that we did with the third thumb in the plasticity lab was a 5-day training study, and that was published back in 2021. So we did 5 days of them training with the third thumb every day for 2 hours, and they also took the thumb home with them. So they really started, over the week, really started to kind of embody it. And what we didn't think that they might, but then we did actually test their embodiment levels across the 5 days and found that after the 5th day of using the third thumb, they did have increased embodiment over it, which I was quite surprised about. So we tested them with a questionnaire. Obviously, embodiment is quite subjective, but I was actually quite surprised by that. And then, it's interesting that you mentioned trust because that is something that's very important, I think, with designing these kinds of technologies. That's why I kind of kept the thumb very soft, so it's always very compliable. But actually, when I do kind of exhibitions with the thumb, I always use foot pads on the floor so people don't have to take their shoes off. And as someone's kind of passing the thumb over to the next person, they might still be standing on the foot pads. And so suddenly the person who's still wearing it, it moves without them controlling it. And they're suddenly like, oh my God, no, take it off. So it is, it can very quickly switch as well.
Yeah. Did you follow up with those people after? Like, did they miss the thumb when it was gone?
Yeah, mixed responses. Yeah, one girl kind of had to have a moment to say goodbye to it. I always felt a little bit bad taking it back. But yeah, this is obviously really crucial with the future of using these kind of technologies, especially kind of in the workplace where it's not perhaps belonging to you and you do have to return it at the end of the day. If you do kind of embody this technology, how does that kind of work in your daily life?
Yeah, definitely. Milia, do you have anything to add?
Yeah, not necessarily on embodiment itself, but on how much people use it. And I think this varies a lot from person to person. Like you were talking about earlier, someone born with one limb might feel more comfortable, might have practiced using only one hand their whole life and are more comfortable without one. And then again, it depends on, the level of the disability, like which prosthesis you can use, because some of the more advanced tech is harder to use depending on how long your residual limb is.
Right, yeah.
So I know some people who, they got the prosthesis, they love it. Like the more tech you can add, they enjoy that and they use it every day as much as they can. And then other people who are far more comfortable without one or using simpler tech because, they trust it more, it's not going to break on them. Depends on what they're used to as well. So yeah, it varies. I mean, I know a veteran who has been using the same arm for like 40 years now, and he's been fine with it until he found out that now he could get a more advanced one, and he got really excited about that. So it really depends on every single person's own situation.
Of course, yeah. Okay, can we get some questions from the audience? We've got an arm up, I see, in the middle at the back there.
Hi, so a few questions actually. First, regarding the prosthetic arm, I noticed it was quite asymmetrical and looked quite heavy. Is there any increased wear, and does that mean that users have to use it less? Say, like I know with sort of prosthetic legs, often it's like half the month it can get up, 2 people can't wear it. Next, with the exoskeleton, is your sort of brain-machine interface part of it entirely external? And if so, how do you sort of deal with like the poor sensitivity and sort of impedance from the skull? And if it's internal, what method do you use to prevent like the brain from rejecting it?
Fantastic, thank you. Okay, let's take the first question first. So I think that was about your prosthetic arm, Milia.
So if I heard correctly, the question was about the weight of the system and the comfort levels of using it day to day. So the system I showed and spoke about is very much in the research stages. I would not recommend anyone take that home. It's heavy, uncomfortable, all these things, and comfort is a huge aspect in general when it comes to prostheses and when it comes to embodiment and usability. So there is a lot of work, I think, commercially, people trying to reduce the weight, reduce the number of motors that are inside. The battery, how small can the battery get? That's one of the heaviest components. And then it also comes down to, they're 3D printing parts now, like how compatible can we make it to these lighter materials? But yeah, definitely my research is very early stages, and it would need a lot of work to get that camera smaller, to get all the parts smaller. Even the wearable EMG, like the EMG that I use is quite technical. We use a lot of sensors, and that's not yet ready to be taken out, but there's a lot of research into making these sensors smaller and more wearable and more usable over time as well.
I don't think there's a wearable a device designer that isn't battling weight. I think if you're using motors, electronics, and especially batteries, I think weight is always an issue. And I think it's so connected to kind of just electronics development just in general, kind of then you have access to kind of smaller and better electronics.
Yeah, so I hope that is getting better over time.
Yes, hopefully.
Fantastic. And then the exoskeleton.
So if I heard the question correctly, I think it was around control intention for the exoskeleton and the extent to which we might use things like brain-computer interfaces. So we do, and in the video that was shown, we were using an EEG, so an electroencephalogram skull cap, to try and record movement intention from an individual. We do that an awful lot because it's non-invasive. Performance isn't necessarily great. It takes a lot of training with a lot of individual. Not everyone can imagine clearly defined movements that we can record and detect. We have also done this with implanted interfaces. Most of my work, that's actually implanting on the spinal cord or on the peripheral nerves, so on things like the median and ulnar nerves in a residual limb. We can record signals from those which would have told the muscles in a limb originally how to move and how to act. So the invasive devices are far more selective and we get higher performance generally, but of course you're having to do a surgery to implant, which comes with other associated risks.
Brilliant. Okay. We have a lot of hands. I feel like I should pick someone from this side of the audience. There's a guy in the red t-shirt.
With your prosthetic sort of finger, do you feel when you take it off that you've actually now sort of lost the body part? Because you seem to be so adept with it.
Yeah. So no, I wouldn't go so far as lost, but yeah, I definitely have felt kind of quite connected to it. I have quite a lot of control over it, and I certainly kind of miss something kind of on my hand. I'd relate it to almost jewelry as well, though. I mean, I think it's quite hard to talk about that because we're not talking about kind of phantom loss or anything like that, which we also study in the Prosthetics lab. So it's I definitely kind of enjoy wearing it and miss it when I take it off. Yes.
Brilliant. Another question, please. Right in the middle there, that row, in the grey t-shirt.
I would imagine to the brain there's a big difference between augmenting an existing limb or replacing one that's lost than adding a completely new one.
Yeah.
Is that the case?
Yes, so that's what we study in the Prosthetics lab. So Professor Svarmaken, my collaborator, is before our collaboration and still, to this day, kind of works on upper limb difference in the brain. So if you're born with one arm or no arms, or she studied amputees, upper limb amputees, and also high-level prosthetic users. And yes, it is a very different kind of study of the brain. And now we look into augmentation. So what happens with a fully occupied homunculus, an able person adds an extra digit, what happens? And so our first study, which we've had the most kind of analysis on, is that the kind of finger representation, so each finger is represented in the brain in the hand area, and we're noticing that after 5 days of use with the third thumb that they kind of collapse a little bit, shift a little bit, and we're not quite sure why. So it is having an impact only after 5 days of use, and that's really interesting. So, and not necessarily kind of a extremely positive thing. So that's why we're really interested in exploring the safety around augmentation devices, especially because I think they are going to kind of be more prevalent in the future. So we're using the third thumb as a model to understand that further. Yeah, so we've just finished data collection on a 7-day training study, and so we're kind of analysing that now. But I will say that people who came in to do the 5-day training study, we then asked them to come in a week after not using the third thumb anymore, and their brain had gone back to the kind of pre-training position. So it's not kind of a lasting effect, but who knows what happens if you wear a kind of extra robotic something for every day for years, what kind of impact that might have. So that's why we're interested in studying it now.
Yeah, amazing. Anything to add? to that? No? It's okay. That's a very comprehensive answer. Brilliant. Okay. The person in the dungarees over there.
Hello, I'm Natalie. I just wanted to ask if you have opinions and you've worked with any babies or toddlers with limb differences from birth, and if that is something that's viable in terms of making tiny ones and getting them to be able to use it and get used to it. Because you mentioned people often, if they haven't been born with them, they then feel alien to them. So if you've worked with any babies and what you think about introducing them to them.
Yeah, not babies, but I have developed a kid's-sized third thumb. So we actually just did a kind of full testing session at the Royal Society Summer Science Exhibition a couple of years ago, and we tested the third thumb, the adult-sized thumb and the kid-sized thumb on 600 participants, and the age range was 4 to 96, and everyone could use it, or 98% of people could use it within the first minute. So so that was kind of testing my size range that fit most kind of kids' hands, and yes, working with kids with upper limb difference, that's on my medical list. So we're exploring people who have recently broken an arm next, and then we're also exploring stroke patients, so looking at augmenting the able hand and playing around with the control mechanism of the disabled arm, and then also kids with upper limb difference. So I've also kind of taken a third thumb to a charity event run by a charity called Reach, and they work with kids with upper limb difference and looking at perhaps developing kind of augmentation technology to create alternative options rather than starting from scratch with a prosthetic on their arm. They can perhaps augment their able hand, and so that's kind of definitely in the works, but not kind of finalised yet. But they're a great patient group to work with. They're really cool, and in the lab we work with kids with upper limb difference all the time.
I mean, it's a really good question, and my view would be that as a research area, it's really under-resourced. Children, as we know, they grow at a tremendous rate. That makes it quite challenging for us to try and engineer a prosthetic that would suit them for a period of time. The way in which prosthetic services are delivered within the UK is challenging in terms of the duration and time to go and visit a clinician and have a device fitted. So one of the projects that we've done recently is evaluate the use of smartphones as at-home scanners of the stump or the residual limb. So instead of having to go into a clinic and have a sort of cast taken, we've shown that you can use the cameras in modern phones to build a 3D model at home. We can then 3D print sockets or designs and send them straight to the home for evaluation. So I think the use of technologies like that will enable us to be much more responsive and able to create customized sockets and prosthetics much faster than we would do at the moment.
So I don't know if now would be a good moment to show off the hand you've been hiding under your chair. Because I know that the part of the hand you've got down there is by Open Bionics, and I believe they've specialised in making prosthetics for children, right?
Yes. So the hand here is a commercial device made by a company called Open Bionics in Bristol. And this is actually largely 3D printed, so it's one of the lowest cost prosthetic hands available on the market. And what we've done with the contraption here is made something called a bypass socket. And this is designed to allow somebody without an upper limb difference to try a prosthetic and experience it. So your hand goes through the wrist mount here, this part straps to your arm, and then what you have is something which you can move around like this. We can put the EMG sensors on the arm, and you can open and close the prosthetic hand and experience what it's really like to try and use one of these devices in your everyday life. And as you say, they make these in different sizes, and they have quite famously made them for children.
Mm-hmm. Fantastic, thank you. Okay, do we have any more questions? I feel like I should give someone at the back the opportunity, but there's some very enthusiastic people in the front as well. The microphone is already there, so I'll let you ask a question.
Hello. So I was asking myself, when you start selling prosthetics, what will be the impact on the society?
Prosthetics or augmentation? Augmentation.
Augmentation, okay. Who wants to try and take that one?
So you might be surprised to know that people already kind of use some augmentation in their day-to-day life. In some factories, you have devices that might help you lift heavier things. Like you're saying, your phone almost feels like an extension of you, and now there are different ways to control it. There are EMG armbands coming out where you can connect to a game. You might be able to control surgery remotely, things like that. But if you're thinking about like additional limbs and things like that, yeah, they'll have some impact on society. I'd say it's adding to what we can do, like you're saying, stabilizing with the thumb or helping patients who need rehabilitation. But for wider users, it's what you would think of in science fiction, but maybe not as extreme as that. So yeah, making you a little bit stronger or helping with specific tasks. So you might be able to do multiple things at a time. But again, it depends on how you're controlling this. It is going to take a lot longer to get to that stage of what you're thinking about. So like with the thumb, you're controlling that with your foot at the moment. But like, what if we could control them without using a movement? What if we could control them by recording different kinds of signals? So we have like some research going on about specific bandwidths of EMG signals that we don't use for movement, but we can still control to an extent. So then could we control an extra limb without moving our hand? So like with the prosthesis, like with what Ben was showing here, I'm moving my arm and then the prosthesis is moving. But what if I wasn't moving my arm? What if it was moving just by me thinking about it? So this is the research areas that we need to start going into to get that impact much wider in society.
So can you put your hand up if you think you're augmented? So for the podcast, I think probably 10% or so of the room have put their hand up. I can see at least 25% of you wearing eyeglasses. I'm wearing contact lenses. Almost all of us are augmented above and beyond what our natural state would be. So in terms of the impact, well, there it is today. I think for me, there's a really interesting debate around the term human augmentation. So I define it as, I mentioned earlier, as rehabilitation, which you could think of as up to what was baseline before accident, injury, disease, loss of eyesight. And then there's the enhancement, which is going above and beyond what baseline would have been for that individual. And that will mean different things for different people. Night vision goggles in a defense setting, that's enhancement. That's improving vision beyond baseline. But there's a spectrum. These are technologies we have now. There are technologies we're developing and we'll see in the future that start bordering more on the science fiction angle. And there are technologies that have traditionally been very focused within healthcare, which is very well regulated and understood, that are starting to merge into that consumer space. So for me, the really interesting impact question is sort of not if, but when, and how do we make sure that we're developing these technologies in an ethically robust way?
Yeah, I guess once a technology reaches a certain level of mainstreamness, if I can use that word, we cease to think of it as technology, right? It's just part of the house. You don't think of a toaster as being technology because most people have one. I guess for me, the biggest societal question I have around these things is access and equity of access. And I think that's got to be something that is a concern.
It's definitely a concern, even now with prostheses.
Exactly.
Like with current technology, not everyone, I mean, I'm talking about like really state-of-the-art moving robotic arms. Not everyone can afford that. There's not enough research into it to make it widespread and things like that. But then you can go into, like you're saying, questions about any technology. If you're going to enhance someone, who gets to be enhanced and who doesn't?
Yeah,
for sure.
Okay, I know there was a very keen person in a green t-shirt somewhere in this region who wanted to ask a question. Do you still want to ask a question?
So, is there anything dangerous with having one robotic finger?
Anything dangerous?
Yeah.
No, not that I can think of right now, but yeah, we're definitely kind of researching the kind of safety of future augmentation devices as well. So how is it going to impact your body in the future is what we're researching with this device.
I guess if you've got an extra, an additional limb, if you've got a tentacle, it could get caught on things.
Yeah, I guess so, yeah.
In the same way that our existing limbs sometimes do.
Yeah.
Brilliant, thank you. Okay, can I have a question from the back? Because I feel like I've been neglecting you up there. There's one right in the middle there at the back.
How can AI technology be used for military?
Now that's a big question.
How old are you? A little beyond our scope.
Yeah, that might be a little out of scope for this podcast episode.
I can try if you'd like.
Have a go if you want to.
So I'm going to talk more generally about what AI can do in this space. And for me, it helps us address one of the biggest challenges, which is the transition from the lab to the home. Or I suppose in terms of your question, from the lab to the battlefield. But maybe we just say lab and out of lab. A lot of the great things that you've seen from us and that you'll see in the media of these sorts of technologies is very optimized to us generally working with one person, training for a long period of time, especially with a brain-computer interface in quite a controlled lab environment. Translating that technology out of the lab, where things are changing, where someone is moving, they're wearing the device in a slightly different position every day, brings with it a lot of challenges. And where we're seeing, I think, the real benefit of AI is in being able to adapt and to learn over time changes to that interface between the technology and the human being.
Talking about different interfaces, so similar to how in my research we're using a camera and we're using the human intention, so there's a lot of machine learning and AI that goes into that, and I can see us moving forwards and integrating different kinds of sensors, intention from the user, information from the environment, and bringing all of that information in together and assessing it and making decisions based on that is technically AI, and that will be more and more useful in these settings.
Yeah, absolutely. Okay, we had a question in the middle at the back row.
My question is, you said earlier that sensitivity means that people can't connect with the hand so much. Is it technologies that could mean people could feel with the robotic hand?
It's a really great question, and there are several. We've worked with relatively simple feedback technologies, so something called vibrotactile feedback or vibration. So we mentioned earlier that your phone or your games controller will vibrate to give you some sensory information. We've done the same thing. So actually on the Open Bionics hand, we put some pressure sensors on the palm and the fingers, and then we put some vibration motors around the residual limb. And so as the hand starts to grip an object, these motors start to vibrate. That works relatively well, but of course it's nothing like the original sensation. So we've also done lots of work on electrically stimulating the nerves in the residual limb, so the median and the ulnar specifically, by putting electrodes either around the arm or sometimes implanted within the arm. Not only can we record the signals that tell us movement intention, we can stimulate those nerves to convey sensory signals. I've tried this myself with surface electrodes. It's quite strange to feel the palm of your hand being stroked when there's nothing actually touching your hand. It does work, but again, translation from lab to home is going to be a big challenge with those kinds of technologies.
Yeah. Okay. We have a question right at the front here.
Yes, thanks. Sort of slightly on the same subject, I was wondering whether these limbs with neural interfaces can affect phantom limb pain.
Great question.
Yeah, it's a very good question. I think the short answer is yes, given the data that's available. If you're providing some sensory feedback, that has been shown to alleviate phantom limb pain. And so for those who not familiar with that term, phantom limb pain occurs in amputees where essentially because the brain and the body are expecting to see sensory information, when they don't, they can create pain, which is called phantom pain. So the limb that is no longer there feels as if it's under tremendous pain, and that really can be crippling pain. And it has been shown that adding sensory feedback can help to alleviate that.
Amazing. We've got a question here on the left.
Firstly, thank you for a very interesting conversation here. Two questions in one, if I may. What has been one of the biggest breakthroughs in the last few years in your specific areas, and maybe what are you expecting in the next 5-10 years to be another big breakthrough?
Great question. Milia, do you want to start?
Yeah, I can start. I think we touched on this earlier. It's about the invasive technology. So it answers both questions, like the breakthrough and where we're going, because it's still early stage technology. And it's a combination of surgical procedures, surgical interventions, as well as getting that EMG technology up to date and more invasive. So when you think of like bionic reconstruction, you have potentially an arm that's attached internally to the rest of the limb with a rod, and inside there you might have a sensor reading the electrical activity at really low levels, so you're getting quite a high density of information. And continuing from there, the technology in terms of how we train that information and the information that we can get from that is really expanding. So you might get lots of different signals coming down through the nervous system, but you don't see them all at once. And so what you can do with the signal is break it down into the different parts and the different movements that you might be affecting on individual muscle fibers. So you're really getting this high density of information and being able to then control the prosthesis. And then it also goes back in terms of sensory feedback. So then if you can internally stimulate some of these muscles, that helps as well. So yeah, it's a mix of things. Surgical reconstruction, the technology itself, the sensors, both ways. And then, of course, you need further developments with the hands themselves. But yeah, that's sort of the direction that research is going in at the moment.
So for me, and I'm going to give a non-technical answer, one of the biggest breakthroughs has been the conversation piece around human augmentation. So it is still quite a new term, but we have seen government policies, white papers, ministry papers, the debate we're having today, it's entering the sort of consciousness as a field of its own right. That's really important, because that then means we can start to answer your question around the 10 years of what really happens when we bring a range of technologies together. And for me, it's that range of technologies that's where lots of the potential is. So the exoskeleton work that's been done in stroke rehab, fab, when we start translating that into workforce where someone's working in a factory, how does that get combined with sensory feedback, with electrical stimulation, with your smartwatch monitoring your vital signs continuously? How's all of that information brought together and used to enhance an individual? So I think that's the exciting 10-year part, is that fusion. The breakthrough now is we're having all the conversations and recognizing that there are some real challenges, both in terms of the technology, but also in the regulation, ethics, and policy.
Yeah, good answer. Yeah, I guess, yes, I agree with everything that's just been said. Also just kind of all the development that's happening around control. I think control is definitely the bottleneck for this kind of technology. Has been for prosthetics for a long time, but also a big challenge for augmentation technology as well. I don't think that kind of true augmentation exists just yet, especially with kind of motor augmentation, like with my thumb, for example. I'm piggybacking off my toes. I'm utilizing my toes. So, I can't run around and use the third thumb. So it's still kind of, there's still an impact on my body. I think, true augmentation exists when it's zero impact controlling purely something extra. So that's kind of where an exciting kind of space will be. And also impact can be also defined as cognitive load. So just because it's perhaps brain control doesn't mean it's perhaps not, a cognitive impact. And then exciting stuff I'm excited about for the future is kind of any material development. So 3D printing, I love kind of working with new materials. This version of the thumb is very, very different from my first prototype in 2017 because of the materials that have now been developed in the 3D printing space. I think really exciting 3D print area is kind of biological 3D printing as well. So in the future, will we be able to design with kind of more biological material rather than just purely kind of mechanical or physical materials? So, and then to be able to kind of, develop that kind of space, which is a bit kind of out there, but it's exciting.
So sci-fi.
Yeah.
Okay, amazing. Gentleman in the blue down here.
Hi, you mentioned earlier about there being a slightly more tricky environment to develop augmentation and robotics. How does the British environment compare to, say, European or American or Asian environments in terms of funding, in terms of accessibility for you guys, and in terms of actually global conversation with everyone around the world who's developing this kind of stuff?
Really interesting question.
That is a really good question. Yeah. And I'm going to try and give a brief answer, if I can. From my own experience, we generally work with European partners and within the larger European regulatory framework. I was speaking at the OECD in Paris a few months ago around neurotechnology regulation, which is sort of pan-European, and thinking about how we create frameworks that we will all operate under in the development of neurotech. That then has quite strong links also to America, to the FDA, who approve lots of their devices. But my view is quite Eurocentric in that sense, because most of my collaborators are European. In the international context, that is a very tricky question. I would just say that there is a lot of variety in regulatory and ethical norms and standards around the world.
Very diplomatic. Anything to add to that?
Just the importance of leaving the lab with these devices. I think you're designing for like humans. It should be able to be used in our human world, not just in the lab. But I think a lot of kind of prosthetics and augmentation devices are used just in the lab. We need to kind of be more inclusive with our testing as well. Different sizes, every type of body that exists should be able to be wearing wearable designs, not just kind of specific few people that it's tested on. So inclusive testing and get out the lab is really important with the future of these devices.
Yeah, absolutely.
I mean, and it's not quite on the regulation and funding aspect, but more on the accessibility aspect. If we're thinking about rehabilitative devices or prostheses used in a healthcare setting, you just have to think about what the healthcare setting looks like here and what that looks like, for example, in the US, and who's paying for what. So who's paying for the device that you're using. So that will affect who gets access to which type of devices.
Yeah, that's a good point. Okay, one more question, and then I'm afraid we'll have to finish up. There's an arm there on the left. I don't think I've taken any questions from that section of the audience yet, so.
Thank you for the very insightful panel discussion. So the research is really kind of, in my opinion, it would help many people who with the physical disabilities, help them have a better quality of life. And just one of the panelists mentioned about, at the research stage, I think there are more funding. But when it comes to implementation stage, there is the IP, and when it comes to the private sector. So for the manufacturing or product development, I think that is might be the challenge for the private sector. But when it comes to end user, for example here, NHS is the largest, the national health, the system that really kind of driving the innovation in healthcare. So at the initial stage, how would you say, even like during R&D stage, when private sectors get involved, but they still need funding, do you think that the government or the NHS would actively got involved in? I have no idea about the a regulatory side of things, but in terms of the funding, how that would work.
Does anybody have any ideas about that?
I can say something. It's a very detailed question.
Yes.
There's probably two sides to this. Developing a medical device is terribly expensive for all the best reasons in the world around the regulation. That can make it difficult to enter a market and to provide and deliver that service. One of the potential benefits of these sorts of technologies entering the consumer space is that they can be manufactured and sold at a lower cost point, because at the moment, the regulatory burden is far less than it is for a medical device. There are all sorts of risks and challenges around the IP and the ethics that might come with that. And if you're taking a technology and selling it in the consumer space rather than delivering it as a regulated medical product, that has lots of issues potentially with it as well. But I think what I'm trying to say is there's sort of a balance here, and I think that there will be benefits from devices being available in other markets that will hopefully make them economic within the medical device sector.
Okay, fantastic, thank you. Unfortunately, that's just about all the time that we have for today. So I'd like to say a huge thank you to my guests, Milia, Ben, and Dani, for joining me for this fascinating discussion. Thank you to the amazing audience for your interesting and insightful questions. And last but not least, I'd like to say a huge thank you to the Great Exhibition Road Festival team and to the staff here at the V&A for having us and for making sure that everything ran smoothly in the background. Thank you again for being here. I hope you have a wonderful weekend and enjoy the rest of the Great Exhibition Road.
Thank you, Claire.
Thanks for listening. If you enjoy Robot Talk, please do share the podcast, subscribe, and leave a review to let us know what you think. This is the final episode of Season 4, so I'm going to be taking a well-earned break over the summer, but I'm thrilled to say that Robot Talk will be returning for a 5th season in September. In the meantime, keep an eye on our website and social media for opportunities to have your say about what topics we should explore in the 5th season, and to send in your questions for my future guests. You can follow us at Robot Talk Pod on pretty much any social media platform you can think of, or check out robottalk.org for all the latest news and updates about the podcast. You can also sign up to our newsletter to be the first to hear about the new season when it launches. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.